Two galaxies can pass through each other without a single star collision. Space between stars is vast, so gravity does the damage. Here is the gist: the crash is gravitational reshaping. Stars mostly miss, while gas clouds slam, compress, then blaze. Galactic collision means two galaxies interact strongly and often merge. This matters because our Milky Way is on course. Andromeda meets us in about 4 to 5 billion years. Your night sky would grow a second whorl, bright and strange. Bottom line, the drama is real, but the smash is subtle. Tilt your view toward two bright cores, drifting closer each night. As distances shrink, gravity grabs the disks and twists their centers. A first pass is a near miss that yanks both galaxies. Tidal forces mean gravity is stronger on the near side. That imbalance stretches arms, raises bars, and launches long tidal bridges. This matters because the first pass decides how dramatic tails become. It also decides whether the galaxies will quickly merge or dance. During the sweep, orbits wobble and stars trade angular momentum. Dark matter halos overlap, creating a shared gravitational well around both. Dynamical friction slows the encounter by stirring surrounding matter. Energy bleeds into random motions, and the pair loses orbital speed. Rule of thumb: longer tails mean a faster and closer pass. Look at the antennae, two spirals colliding about 45 million light-years. Their tidal streams arc over 200,000 light-years into space. Star clusters sparkle along the bridges, like beads on stretched taffy. Gas lanes kink across the cores, hinting at bars forming inside. Simulations matching those tails recover a fast, grazing first pass. Net result: the first meeting sets the stage for everything. It plants bars, tosses stars, and stretches matter into ribbons. From here, the pair cannot forget, and gravity keeps pulling. They will return for another pass, closer and more violent. Threaded gas streams crash together where the disks overlap and shear. A starburst is a brief surge in stellar birth rate. It matters because one outburst can forge billions of new suns. Colliding clouds create shocks that squeeze gas into dense knots. Pressure rises, turbulence thins support, and gravity finally wins. Massive stars ignite, blow winds, and carve glowing bubbles through dust. Supernovae then stir the soup, but also trigger fresh collapse. Gas consumption accelerates, while radiation pushes material outwards. Example in real terms: ARP-220 forges about 200 suns yearly. Its core hides double nuclei within thick, glowing dust. Temperatures soar, and infrared light pours out like a furnace. The antennae host thousands of young clusters, some superstar clusters. Many weigh over 100,000 solar masses each. Observations catch shock fronts, traced by hydrogen lines and X-rays. Cold gas maps show streams feeding the central kiloparsecs. Rule of thumb: more gas inflow means brighter and shorter bursts. Eventually, feedback blows out or heats the leftover fuel. Bottom line: smashed gas makes stars fast, then self-regulates hard. The blaze can fade within a few 100 million years. What remains is a packed core and spent outer streams. Down the stretched arms, rivers of gas stream toward each core. An active galactic nucleus is a black hole feeding brightly. It matters because one nucleus can outshine every star combined. Gravitational torques drain spin, letting gas lose angular momentum. Gas funnels inward, heats up, and forms a glowing disk. Magnetic fields launch winds or jets that punch through clouds. Radiation pressure can clear paths or choke future star formation. NGC 6240 shows two active cores, about 3,000 light-years apart. Their X-rays flicker, signaling gas tumbling onto both monsters. Peak quasars radiate about 10 to the power of 39 watts. That is about 1 trillion times the sun's output. As distances shrink, the black holes will eventually spiral together. They shed energy to stars and gas, tightening their orbit. The final plunge releases gravitational waves in space itself. Lisa could hear those ripples from merging million solar mass giants. Cavities and cones appear where jets shove matter aside. Nearby gas cools differently, steering where new stars can grow. Bottom line: collisions feed black holes, and black holes fight back. Sometimes the nucleus blazes first, then the starburst follows. Other times, winds quench the burst, leaving a quiet core. Set a clock because galaxy collisions run on slow time. A merger timescale is the span from first pass to coalescence. You care because it tells us what sky changes we witness. Orbits decay as halos and stars steal energy from the pair. Each close sweep tightens the path, shortening the next loop. Gas drags help too, especially in dense central regions. Big spirals might merge within 1 to 2 billion years. Smaller companions can be swallowed in a few hundred million. The mice likely passed 90 to 200 million years ago. Their streaked tails record the timing like slow-motion handwriting. Milky Way and Andromeda first graze in about 4.3 billion. Full coalescence likely finishes between 6 and 8 billion years. Tiny test would your descendants see motion, barely across lifetimes, but telescopes catch it by mapping stars over decades. Proper motions nudge, revealing Andromeda's inbound path with precision. One-sentence recap: mergers are slow but relentless once begun. The sun completes millions of orbits before the galaxies settle. Night skies bloom gradually, season by season, generation by generation. Meanwhile, tidal tails fade as stars disperse along great loops. Gas piles inward after each pass, feeding bursts and nuclei. Bottom line, cosmic patience pays, the end state is unavoidable. Step outside in 4 billion years and the sky is busy. A second spiral spans the darkness, brighter than the Milky Way. The local group's giants are approaching, Milky Way and Andromeda. This is our neighborhood's major merger, unfolding over billions. Expect a slow ballet, not a doomsday firestorm across space. Gravity will stretch both disks and throw great tidal loops. Gas clouds collide, lighting bursts near the joint inner region. Our sun likely avoids impacts because stars are tiny targets. Estimates put direct hit odds effectively 0 for our system. However, orbits can shift and the sun may migrate outward. It could end up tens of thousands of light years farther. Triangulum might join briefly, stirring the dance even more. Tides may thicken the disk and puff up stellar motions. Nighttime shows glowing bridges and knotted star-forming regions arcing overhead. Oceans and daylight barely notice because gravity works gently here. Bottom line, the show is spectacular and life continues. After several passes, both galaxies will share a common envelope. Their black holes will drift inward, circling inside a star swarm. When they finally merge, ripples of spacetime roll across space. Eventually, the remnant relaxes into a rounder, calmer galaxy. One-sentence recap: our skies transform, but worlds remain mostly undisturbed. Debris fades and the chaos cools into a new shape. A merger remnant is the galaxy that survives the collision. It matters because many ellipticals likely grew this exact way. Stars lose ordered rotation and gain random, hot motions. Astronomers call that violent relaxation, a fast orbital reshuffling. Gas either turns into stars or heats and escapes as winds. Without fuel, starbirth slows and colors shift toward red. Shells and ripples linger where streams wrap around the core. NGC 1316 shows layered shells across tens of thousands of light years. Its stars speed around at roughly 200 kilometers per second. The central black hole grows heavier from the earlier feeding. Over time, dust settles and the remnant looks smoother. Globular clusters swarm the halo, some formed from shocked gas. Kinematically decoupled cores can mark where two centers once twirled. Bottom line, the wreck becomes a rounder system with quieter growth. Hot gas halos glow in X-rays, whispering past outflows. Stellar populations age, raising the average mass of dying stars. If fresh gas arrives later, disks can regrow in pieces. One-sentence recap: mixing scrambles orbits, and star birth winds down. Not every crash ends the same, surprises pop up often. A collisional ring happens when a smaller galaxy punches through. It matters because these rings are laboratories for star formation. A wave sweeps outward, compressing gas into a bright circle. Behind the ring, gas is left depleted and calmer. The cartwheel stretches roughly 150,000 light-years wide. Blue knots sparkle along the rim, tracing newborn stellar clusters. Polar rings can form when material settles around a tilted axis. Those structures spin perpendicular to the host, like a cosmic gyroscope. Tidal dwarfs are small galaxies born inside long tidal tails. They can reach hundreds of millions of solar masses each. Some keep forming stars long after the main event ends. Common mistake is thinking collisions always destroy disks forever. Gas can redistribute, and new disks sometimes regrow later. NGC 4650A hosts a majestic polar ring wrapping the core. Its geometry reveals past accretion along a misaligned path. Tiny tests spot the ring by the blue star chains. Bottom line, collisions remix matter into rings, dwarfs, and oddities. Edges can sparkle for hundreds of millions of years. Meanwhile, the central region grows quieter as fuel is spent. Later interactions may twist these features into shells or streams. One sentence recap: not all outcomes are ellipticals, variety thrives. So we began with a weird claim about no star crashes. Now you have the picture: gravity does the wrecking. Galaxies stretch, gas collides, stars ignite, and black holes feed. Tails fade, orbits mix, and calmer remnants take their place. Our own sky will change, slowly and beautifully over eons. If that landed, join me for more clear space stories. Thanks for watching, and look up tonight for practice. The universe moves slowly, but its stories reward patience. See you in the next chapter, somewhere between galaxies.